Experimental study on harmonic mitigation in a grid-connected solar power plant. Abstract solar energy is converted into electrical energy through the use of solar power plants. Solar power plants have a photovoltaic array, a maximum power point monitoring unit, a DC to DC converter and, typically, a multi-level inverter. In these types of devices, power filters are used to counteract harmonics. The trouble with active power is that it adds expense to an otherwise costly solar power plant. Keyword: solar power plant, harmonic mitigation, power quality, power filter. Introduction. Harmonics are introduced in the system due to extensive use of power electronic converters as well as due to nonlinear loading on the grid side. Harmonics can also be introduced into the system due to lightning discharges and switching. Here we are focused on the mitigation of harmonics generated due to converters and nonlinear loads. The harmonics introduced into the system will eventually lead to the following harmful effects. Overheating of windings present in generators, transformers, and measuring pieces of equipment. Early degradation of power cables. Interference with power line carrier communication and other electronic devices. Therefore, mitigation of harmonics is an essential part of an optimum functioning power system. Mitigation of harmonics also leads to lower downtime and therefore increased consumer satisfaction, which eventually leads to higher profit margins. There are at least 6 types of filters which are used for harmonic mitigation. We are mainly concerned about harmonic mitigation in the grid-connected solar power plant. Extensive literature review of the past 10 years helps us to ensure that there is almost no article that compares and summarizes harmonic mitigation techniques, especially for a solar power plant. The motivation behind this paper can be summarized as follows. To act as a helpful guide for design engineers, consultants and customers concerning solar power plant. To provide comprehensive details regarding harmonic mitigation techniques so as to increase the profitability and efficiency of a solar power plant. Harmonic mitigation through the use of passive power filters. Passive filters use passive components, such as inductors, capacitors, and resistors. These cannot increase the signal energy. The frequency range for harmonic filters is limited to approximately 3000 Hz. It is common to characterize the frequency selective filters with respect to their passbands. Double-tuned filter. A double-tuned filter is derived from 2 single-tuned filters and is shown in Fig 1. The advantage with respect to 2 single-tuned filters is that the power loss at fundamental frequency is less and 1 inductor instead of 2 is subjected to full impulse voltage. This is an advantage in HV applications. 2 single-tuned filters of different frequencies into a single double-tuned filter. Double-tone filter and 2 parallel single-tone filters have the same feature that each of them will filter 2 distinct frequency harmonics. Basically, it filters out only 2 different frequency harmonics, so it acts as if 2 single-tuned filter are connected together. Mathematical explanation about the working of a double-tuned filter is given below. Where generally, R1 is omitted and R2 and R3 are modified so that the impedance near resonance is practically the same. Note that inductor L1 will have some resistance, which is considered in the above equations. High-pass filter. The above figure depicts a typical high-pass filter. It works according to the frequency impedance characteristic of the capacitor. A high-pass filter, HPF, is an electronic filter that transmits signals with a frequency greater than a certain cut-off frequency and attenuates signals with a frequency lower than the cut-off frequency. The sum of attenuation for each frequency depends on the configuration of the filter. Typically, a high-pass filter is modeled as a linear time invariant system. In the field of audio engineering, it is often called a low-cut filter or a bass-cut filter. High-pass filters have many applications, such as DC blocking from circuits vulnerable to non-zero average voltages or radio frequency systems. They can also be used in combination with a low-pass filter for the production of a band-pass filter. Mathematical explanation of a high-pass filter is given below. Single-tuned filter. The single-tuned, ST, filters are efficient filters and will bypass a certain harmonic to which these are tuned. These are most widely used filters in all applications of harmonic mitigation. However, care is required in their design, so that the components are not overloaded, and overvoltages due to their applications are controlled. Many times a group of ST filters are applied, each tuned to a specific frequency. The operation of an ST shunt filter is explained with reference to Figure 3. Harmonic current injected from the source through impedance ZC divides into filter and system equivalent impedance ZEC. This system impedance can be found by circuit reduction. This is in fact the short circuit equivalent impedance. Care is taken in their design so that the components are not overwhelmed and the overvoltage due to their application is regulated. This device impedance can be found by circuit reduction, which is actually a short circuit impedance counterpart. The current is divides into two parallel paths with magnitude as IH and IV. Harmonic mitigation through the use of active power filters. Basically there are two types of active power filters, namely 1. Series active power filter and 2. Shunt active power filter. Active power filters, APF, are filters, which can perform the job of harmonic elimination. Active power filters can be used to filter out harmonics in the power system which are significantly below the switching frequency of the filter. The active power filters are used to filter out both higher and lower order harmonics in the power system. The main difference between active power filters and passive power filters is that APFs mitigate harmonics by injecting active power with the same frequency but with reverse phase to cancel that harmonic, where passive power filters use combinations of resistors, R, inductors, L, and capacitors, C, and does not require an external power source or active components such as transistors. This difference make it possible for APFs to mitigate a wide range of harmonics. Let us examine in detail the two filters. Series active power filter. A voltage VF is injected in series with the line and it compensates the voltage distortion produced by a nonlinear load. A series active filter is more suitable for harmonic compensation of diode rectifiers where the DC voltage for the inverter is derived from a capacitor, which opposes the change of the voltage. Shunt active power filter with D space. The voltage distortion in a weak system is very much dependent on harmonic current, while a stiff system of zero impedance will have no voltage distortion. Thus, provided that the system is not too stiff, a non-sinusoidal voltage can be corrected by injecting proper harmonic current. A harmonic current source is represented as a Norton equivalent circuit, and it may be implemented with a pulse width modulation, PWM, inverter to inject a harmonic current of the same magnitude as that of the nonlinear load into the system, but of harmonics of opposite polarity. A shunt connection is shown in Figure 5. The load current will be sinusoidal, so long as the load impedance is higher than the source impedance. The subscript H signifies harmonic component. If the following equation is satisfied, then in Figure 5.2. If the shunt active filter is controlled such that, then source current is, in order that the source current becomes sinusoidal. Then, however, these conditions cannot be satisfied. K should be large, and impedance on the load side should be small for harmonics in order to suppress the source harmonic current. This cannot be satisfied for a conventional phase-controlled thyristor rectifier, and ZL is almost infinite. The required output voltage Vc also becomes infinite. In Figure 5.2, for series filter compensating a harmonic voltage source, the current is, when K is much greater than 1 pu, is 0. To realize a large gain, a hysteresis or ramp comparison control method can be used. 3. Methodology and experimentation. For detailed model of the experimental setup, please visit Model for Harmonic Mitigation. Experimental setup. The power system consists of a solar PV array connected to a three-phase 500V grid with a fundamental frequency of 60 Hz. The power GUI block is a discrete block with sample time 33 microseconds. Measurement and metering subsystem contains block that measure active power, kW, reactive power, kVAR, power factor, total harmonic distortion and maximum power point tracking measurements. The grid-connected system is connected to a wider independent grid, usually a public utility grid, which feeds energy directly into the grid. This energy can be exchanged by a residential or industrial building before or after the revenue assessment stage, depending on whether the attributed energy output is measured independently of the energy usage of the consumer, feed-in tariff, or only on the difference in energy consumption, net metering. The detailed diagram of the solar PV array has been described below. A 100 kW PV array is connected to a 25 kV grid via a DC-DC boost converter and a 3-phase 3-level voltage source converter, VSC. Maximum power point tracking, MPPT, is implemented in the boost converter by means of a Simulink A registered trademark model using the incremental conductance and integral regulator technique. Another example, C-power_Barre_grid_average model, uses average models for the DC_DC and VSC converters. In this average model, the MPPT controller is based on the perturb and observe technique. The detailed model contains the following components. 1 PV array delivering a maximum of 100 kW at 1000 W/M2 sun irradiance. 2.5 kHz DC-DC boost converter increasing voltage from PV natural voltage, 273 VDC at maximum power, to 500 VDC. Switching duty cycle is optimized by a MPPT controller that uses the incremental conductance and integral regulator technique. This MPPT system automatically varies the duty cycle in order to generate the required voltage to extract maximum power. 3.1980 Hz 3-level 3-phase VSC. The VSC converts the 500 VDC link voltage to 260 VAC and keeps unity power factor. The VSC control system uses two control loops. An external control loop which regulates DC link voltage to +/250 V and an internal control loop which regulates ID and IQ grid currents, active and reactive current components. ID current reference is the output of the DC voltage external controller. IQ current reference is set to 0 in order to maintain unity power factor. VD and VQ voltage outputs of the current controller are converted to 3 modulating signals UOB_ref used by the PWM generator. The control system uses a sample time of 100 microseconds for voltage and current controllers as well as for the phase locked loop, PLL, synchronization unit. Pulse generators of boost and voltage source converters, VSC, use a fast sample time of 1 microsecond in order to get an appropriate resolution of PWM waveforms. 6.10 kVAR capacitor bank filtering harmonics produced by VSC. 7.100 kVA 260V/25 kV 3-phase coupling transformer. Utility grid, 25 kV distribution feeder plus 120 kV equivalent transmission system. The 100 kW PV array uses 330 SunPower modules, SPR305E/D. The array consists of 66 strings of 5 series connected modules connected in parallel, 665305.2 W equals 100.7 kilowatts. The module parameter of the PV array block allows you to choose among various array types of the NREL System Advisor model, https://sam.nrel.gov/. The manufacturer specifications for one module are: number of series connected cells, 96. Open circuit voltage, VOC equals 64.2 V14. Short circuit current, ISC equals 5.96 A. Voltage and current at maximum power, VMP equals 54.7 V, IMP equals 5.58 A. The PV array block menu allows you to plot the IV and PV characteristics for one module and for the whole array. The PV array block has two inputs that allow you varying sun irradiance, input 1 in W/M2, and temperature, input 2 in degree C. The irradiance and temperature profiles are defined by a signal builder block which is connected to the PV array inputs. The solar PV array has been connected to a grid with 2 unbalanced and 1 balanced load. the details of which has been given below. The first load is an unbalanced load connected with a series active power filter for harmonic mitigation. It consists of a universal bridge with snubber resistance of 100 ohms, and snubber capacitance of 0.212 mF. The second load consists of a three-phase bridge configuration diode rectifier with unstate resistance of 0.1 ohms. The passive power filters are Simulink, a registered trademark model. Named passive harmonic filter, they are configurable as single-tuned, double-tuned, and as a high-pass filter. When the currents on the three live wires of a three-phase system are not equal or are not at an exact 120 degree phase angle, the power loss is greater than for a perfectly balanced system. The method of symmetrical components is used to analyze unbalanced systems. The above block diagram, figure 9, is named as load_2_ with _shunt_active_power_ filter and can be subdivided into shunt active power filter and non-linear load. An additional power GUI block, discrete, is present here with sample time of 5 microseconds. The shunt active power filter is based on PQ theory and contains a D-space block for additional simplicity. The above block diagram, figure 10, describes block named as load_1_ with _series_active_power_ filter. This block consists of a non-linear load and a series active power filter. Methodology. The simulation is performed in Simulink, a registered trademark, with time of simulation being from 1 second to 2 seconds. The solver used to simulate is ODE4, Runge-CUDA, with step size as fixed. The format for input and output data is set to array and maximum number of data points is set to have value of 1000. All the other solver parameters contain default values. A fast Fourier transform, FFT, is an algorithm that computes the discrete Fourier transform, DFT, of a sequence, or its inverse, IDFT. Fourier analysis converts a signal from its original domain, often time or space, to a representation in the frequency domain and vice versa. The currents and voltages of which fast Fourier transform, FFT, analysis has been done are listed in the following table. The simulations are performed such that only one filter is active at a time or none of the filters are active in the given time interval. The sequence of which would be as follows: A. No filters are connected. Only shunt active power filter is connected. 3. Only series active power filter is connected. 4. Single tuned passive filter is connected across load 1. 5. Double tuned passive filter is connected across load 1. 6. High pass filter is connected across load 1. 7. Single tuned passive filter is connected across load 2. 8. Double tuned passive filter is connected across load 2. 9. High pass filter is connected across load 2. The single-tuned filter connected across load 1 is tuned for 5th harmonic frequency, while double-tuned filter has been tuned for 5th and 7th harmonic. The high-pass filter connected across load 1 has a cut-off frequency of 180 Hz or 3rd harmonic. The single-tuned filter connected across load 2 is tuned for 2nd harmonic, while the double-tuned filter is tuned for 2nd and 5th harmonic. The high-pass filter connected across load 2 has a cut-off frequency of 120 Hz of 2nd harmonic. Result of simulation. With no filters connected to load 1, the following waveform of load current and load voltage are obtained. 6. Conclusion. The below table compares total harmonic distortion for various configuration of filters. Passive power filters perform best when tuned properly, but they are unable to compensate for the DC component of current/voltage waveform. Active power filter perform best in almost every scenario, but series active power filter is best used for mitigation of voltage sags than harmonic mitigation. If not tuned properly, then passive power filters can act as a harmonic source rather than harmonic sinks.